Welcome, everyone. Thank you for joining me as we begin our discussion on the future of system design. Today, we are exploring the 2026 Architectural Standard, with a specific focus on modern database selection and optimization. This session is based on the insights shared in the Phuong Lei Dispatch. As we look ahead, understanding how to align data storage solutions with evolving performance requirements is more critical than ever. Let's dive into the strategies that will define the next generation of architectural excellence.
The Efficiency Manifesto defines a critical paradigm shift in systems design. Complexity is the enemy of scale, and the era of distributed clusters is ending. Looking at legacy fragmentation on the left, we see how component chaining and extensive glue code create a tangled, fragile environment that slows development and limits growth. We are moving instead toward unified efficiency. By utilizing purpose-built powerhouses, we replace this fragmented complexity with a streamlined and cohesive architecture. This approach eliminates the overhead of legacy systems, providing a direct path to high-performance, scalable infrastructure. High-performance analytics, or OLAP, requires specialized tools to handle specific data demands effectively. When we look at interactive queries, the industry is shifting away from traditional cloud data warehouses like BigQuery, Snowflake, and Redshift. In their place, we recommend adopting ClickHouse. The primary reason for this transition is ClickHouse's ability to provide the ultra-low latency required for truly interactive analytics and real-time dashboards. On the other side of the spectrum, we have distributed SQL. For these workloads, we are moving beyond the older stack of Spark, Hive, and Presto. The modern choice is Trino. Trino is engineered specifically for high-speed distributed SQL execution directly over data lakes, offering significant performance improvements over its predecessors. By making these strategic shifts, organizations can achieve much faster insights and more efficient data processing. The DuckDB ecosystem provides a streamlined approach to data processing, whether you are working locally or in the cloud. For local workloads, it is time to move beyond the combination of SQLite and Pandas and start using DuckDB. DuckDB is purpose-built for fast, local analytical SQL, delivering exceptional performance for complex queries on your own machine. For cloud analytics, we can simplify our infrastructure by moving away from S3, Athena, and Glue, and starting with MotherDuck. MotherDuck offers managed DuckDB in the cloud, providing a cohesive and powerful environment for your data analysis needs. The PostgreSQL convergence represents a strategic shift toward consolidating data infrastructure to reduce operational complexity. Many teams are moving away from maintaining separate instances of MongoDB for documents and Elasticsearch for search, opting instead to leverage PostgreSQL. Because PostgreSQL natively supports both JSON-B and full-text indexing, it allows us to manage document and relational data together within a single ACID-compliant system. Additionally, there is a clear trend toward migrating Airflow metadata from MySQL to PostgreSQL. This transition ensures a more reliable and robust management of workflow states, capitalizing on PostgreSQL's superior handling of concurrent transactions and complex data integrity. By centralizing these diverse requirements onto PostgreSQL, organizations gain a simpler architecture without sacrificing performance or specialized functionality. Let's dive into how we can better achieve horizontal scale and throughput by modernizing our database strategy. Starting with distributed SQL, we want to move away from the complexities of MySQL sharding and the use of proxies. Instead, we are looking towards TiDB. The primary advantage here is native horizontal scaling, which simplifies operations and removes the manual overhead traditionally associated with sharding. Moving to high-throughput workloads, it is time to reconsider large Cassandra clusters. By transitioning to ScyllaDB, you can achieve superior performance while requiring fewer nodes to manage. This consolidation leads to a more efficient and less resource-intensive infrastructure. Finally, for wide column storage, we recommend moving away from the HBase and Hadoop ecosystem. By starting with Bigtable, you gain the benefits of managed simplicity. This fully managed service allows you to scale effortlessly without the operational burden of maintaining a complex self-hosted cluster. These shifts are essential for building a scalable and sustainable data platform. Moving into infrastructure and coordination, we are refining our stack to reduce complexity and improve consistency. For our streaming clusters, we are transitioning away from the traditional Kafka and Zookeeper combination in favor of Redpanda. The primary advantage here is that Redpanda functions as a single binary while maintaining full Kafka compatibility, which significantly streamlines our deployment and operational overhead. In terms of service coordination, we are replacing Zookeeper and Consul with etcd. We have selected etcd because it offers a simpler implementation while providing the strong consistency required for reliable distributed coordination. These shifts allow us to move toward a more modern, efficient, and easier to manage infrastructure. Efficiency and embedding serve as the core pillars of our architectural evolution. When addressing caching under high-load scenarios, we are moving away from the legacy overhead associated with Redis and Memcached. In their place, we are implementing Dragonfly. This transition is driven specifically by its extreme memory efficiency, which optimizes throughput and resource utilization. In parallel, for our embedded key value requirements, we are discontinuing the use of custom wrappers around RocksDB in favor of BadgerDB. This move is strategic, as BadgerDB provides a pure Go implementation, ensuring seamless integration and improved maintainability within our existing development stack. When we look at the current observability landscape, many organizations find themselves managing a complex array of tools, such as Loki and Elastic for logging, alongside Prometheus, Thanos, and Mimir for metrics. This fragmentation often leads to increased operational overhead and significant storage challenges. As illustrated here, we advocate for a more streamlined approach by consolidating these disparate data streams. By switching to Victoria Logs, you gain a high-performance solution specifically designed for high-volume, centralized log storage. For your time series data, transitioning to Victoria Metrics offers long-term retention and superior scalability without the traditional complexity of legacy systems. This unified approach provides a more cohesive and efficient observability stack that scales effortlessly with your infrastructure's needs. In the realm of observability, managing time series data efficiently is critical. We recommend moving away from the complexities of InfluxDB and the manual burden of managing custom rollups. Instead, transition to TimescaleDB. The value proposition is clear. There is no need to learn a new proprietary query language. By using standard SQL for your time series analytics, you can leverage existing expertise and streamline your data infrastructure for better performance and ease of use. As we navigate the evolving landscape of search and AI vectors, our architectural choices must adapt for better performance and simplicity. In the domain of application search, we recommend moving away from resource-heavy solutions like Elasticsearch and Solr. Instead, shift toward Meilisearch, which provides a lightweight alternative with exceptional out-of-the-box ranking capabilities. For vector similarity tasks, we suggest transitioning from platforms like Pinecone and Milvus to Qdrant. Qdrant stands out by offering more efficient vector services, ensuring high performance for your AI-driven search applications. In the realm of graph processing, we are advocating for a significant shift in infrastructure. It is time to move away from complex Neo4j clusters and transition toward Memgraph. The competitive edge provided by Memgraph is its superior speed, achieved through optimized in-memory graph processing. This approach allows for the rapid analysis of highly interconnected data structures, providing performance levels that traditional clustered systems struggle to match. The 2026 reference architecture represents a unified ecosystem meticulously designed to prioritize low latency and operational simplicity. At the summit, the analytics layer leverages high-performance engines such as ClickHouse, MotherDuck, and Trino to deliver rapid, data-driven insights. Below this, the operational backbone serves as the engine room of the stack, utilizing Postgres and TiDB for relational consistency, ScyllaDB for scalable NoSQL storage, and Redpanda for high-throughput event streaming. The base of the architecture is defined by observability and infrastructure, where Victoria Metrics handles sophisticated monitoring, etcd manages distributed coordination, and Dragonfly provides an ultra-fast in-memory data store. Spanning across these horizontal layers is the intelligence vertical. By incorporating Qtrant for vector search and Meilisearch for lightning-fast indexing, this architecture ensures that AI and advanced search capabilities are deeply integrated into the entire data lifecycle. This modular yet cohesive framework is built to meet the rigorous performance and scalability demands of the next generation of applications. Complexity is optional. In our drive for scalability, we often introduce layers that hinder rather than help.
It is essential to audit your current stack and identify where simplification can occur. By replacing complex clusters with single, high-performance nodes where appropriate, we can strip away technical debt and architectural bloat. Focus on streamlining your infrastructure to build for maximum speed and operational clarity.